Setting it all up can take anything from a few days to a couple of weeks. The choice of site for drilling an exploration well isn't ours. It's made by the geologists from their knowledge of the rocks that lie below, 3 kilometers or more beneath our feet. A classic choice would be over a dome-shaped fold in the rock layers, revealed by seismic survey. But in this business, a choice is a gamble. The chance you're counting on is that oil and gas, formed somewhere in the vicinity millions of years ago, could have migrated into the dome through layers of permeable rock and have accumulated there, hemmed in by an impermeable layer above. Once there, they would have separated. The gas on top of the oil with groundwater around the flanks, all of them at high pressure. Well, that's what we hope has happened, but it's going to take up to 8 weeks to prove it. We start with a relatively large bit to drill through the soft surface layers, down to 300 meters or so. When your target is over 3 kilometers down, you don't just sink a deep hole. You build it carefully, stage by stage. The drill is driven from the surface, turned by a rotary table on the platform, the drill string suspended from the tower. Down below, the teeth of the drilling bit pound the rock into fragments. They'd soon choke the hole unless we'd a way of flushing them out. What we use is a special drilling fluid, pumped down the drill pipe to cool the bit and carry the cuttings away, back to the surface. The mud, as we call it, is channeled out over fine mesh screens, the shakers, to remove the coarse cuttings, and then passed through centrifuges to get rid of the finer stuff, before it's recycled back down the hole. As long as the drill is turning, the mud must be kept circulating. But every 10 meters, drilling has to stop to add another section of pipe. It's a tough job, and it calls for some slick coordination from the floor crew. But they all get plenty of practice. On an average well, they'll add pipe over 300 times before they reach hole bottom. Everything's done to a schedule, supervised by the tool pusher. Nowadays, he doesn't push anything but the drilling program. He's responsible, among other things, for calling up supplies of materials as they're needed and making sure they arrive on time. This steel casing, for instance, will be run into the hole when the drill has reached 300 meters. It's essential to stabilize the well at this stage to prevent it caving in. This will be the next job coming up on his program within the next few hours. The casing, like drill pipe, is assembled section by section, and each of them weighs a couple of tons. These spacers are fitted at regular intervals to keep the casing central in the hole as it goes down. The casing is lowered in until its nose reaches a point just above the bottom of the hole. The next job is to cement it home. The cement is a wet slurry, pumped down the inside of the casing under pressure. Downhole, it breaks through a seal in the nose and is forced round the outside of the casing back to the surface, pushing the drilling mud out ahead of it. Once enough cement to anchor the casing has been pumped in, it's followed by drilling mud, ready for when drilling starts again. The pumps are then stopped and the cement given time to set. Now we can cap the top of the casing with a set of safety valves, known for obvious reasons as the blowout preventers. If further drilling were to encounter high-pressure gas or water, we could get a blowout. To contain it, we need a means of sealing off the hole at the surface. It's done by hydraulic rams that close off the gap between the drill string and the inside walls of the casing. The deeper we go, the higher the pressures, and more powerful ram seals will be fitted as the hole progresses. Once the blowout preventers are fitted, drilling can continue safely to greater depths. But what if we were drilling not on land, but way out at sea? Our rig would be on a floating platform, anchored 150 meters or more above the drill hole. But we'd still have to follow the same procedures. On a marine well, blowout preventers are every bit as vital, but they have to be fitted by remote control, sent down on guide wires and locked onto the casing under the watchful eye of the television camera. On top goes a marine riser, a conductor tube to connect the rig directly to the drill hole down below. This gives us the closed system we need for running pipe and circulating mud, just as if we were working on land. As drilling goes on, the mud return shows the succession of different rock layers we're passing through. Some of them could contaminate the mud and prevent it functioning properly, so we need to keep a constant check on its composition. The mud is also to be maintained at a given viscosity. We don't want it altered by anything getting in from the rocks we're drilling through. As well as viscosity tests, we have to check for chemical changes. If we were to hit a layer of salt, for instance, we could be in deep trouble. The mud would cease to lubricate the drill string and fail to plaster the walls of the hole. They could collapse and jam up the works completely. We'd have to replace the mud with a new supply of an entirely different composition to neutralize the salt. Up on the platform, an equally close eye is kept on the behavior of the bit. Cutting through hard rock, its life is usually less than 12 hours. Loss of cutting power shows up on the driller's control dials, and it makes a distinctive noise. Nothing for it but to pull the whole string, 30 meters at a time, and stack it up the tower.
Thank you.
We can have anything up to 100 stands of pipe in the rack before we reach the bit. Maybe 8 hours to recover it. Another 8 to run the new one in again. Changing a bit is time-consuming, but part of the normal program. But drilling can sometimes hit problems that are totally unpredictable. Conditions downhole might suddenly change and affect the consistency of the mud. If it got too thick, it could bind the drill tight, and that could be drastic. If it happens, you just pull out what you can, then you go fishing, and with luck, you make contact. But if the hole itself collapses, you abandon the jammed-in section and recover the rest by breaking the pipe. You can't drill back down through the blockage. You have to bypass it, using special deviation equipment, offsetting a new hole at a predetermined angle. Mechanical troubles don't happen all that often, but on every well you have to be prepared for hazards of another kind that may lie buried in the rocks below. A sudden build-up of pressure in the mud line. Stop drilling, back off the drill, and seal off the well at the surface. Everything's shut down. The pressures are measured and the pumps are restarted slowly while the cause of the build-up is identified. We've encountered a pocket of gas trapped in a shallow lens of sandstone. It's leaking into the drill hole and forcing out the mud. Before we can drill on through the pocket, we have to counteract the pressure by pumping down a heavier mud. This is usually kept in the storage tanks, ready for just such an emergency. A 1,000 meters below, the gas is frothing into the hole. But as the new mud begins to circulate, the pressure is gradually neutralized, and a special sealing compound plasters the walls of the hole. As the pressure returns to normal, the emergency is over. Drilling can start again, with the mud sealing off the rest of the gas zone, till we can line the hole with another run of steel casing. Then, with a smaller bit, on towards the target. Still a long way to go. As the drill bites through the cap rock and approaches the target zone, its progress is monitored meter by meter. Inspection of the cuttings will give us the first indication of what really lies below the cap rock, whether or not the choice of drill site was justified. It's sandstone, all right, and that could be oil. Under the microscope, the sample certainly looks promising. Coarse-grained sand with a definite dark stain. If it's oil, it'll glow yellow under ultraviolet light. It's there, all right, but so far only a trace. Not until we've drilled all the way through the formation can we begin to assess its significance. To find out what's down there, we run a probe. The probe is an electronic device that responds to variations in the electrical, acoustical, and radioactive properties of the different rock layers, and transmits its measurements back to the recording truck on the surface. As it passes back up through the formations, it will identify the nature of the rocks in the immediate vicinity of the drill hole and indicate what they contain. Shale. Porous sandstone, saturated with oil. Even more porous here. Limestone, nothing much there. Then the gas layer, and finally the impermeable shale of the cap rock. We know there's oil and gas down there. But there's a lot to do yet before we've any idea how much. It certainly looks promising, encouraging enough to justify a flow test. The hole has been cased right down to the basement and cemented in. A flow tube is now run into the oil zone and set about halfway down. To get at the oil, we have to perforate the casing. We do it by firing a string of bullets. The oil begins to flow as the pressure in the well is reduced. The flare-off of gas that comes up with the oil signals a successful test. To get this far has cost anything from £300,000 on land to a couple of million offshore. Yet all we've managed to assess is the potential of the area immediately around a single drill hole. What interests us now is the rest of the structure. To find out the full extent of the oil reservoir, we have to sink more wells. The first outstep has hit groundwater, and we can now deduce the profile of the reservoir in this direction. Next, we sink a third well in line with the other two. This again hits groundwater and completes the profile, the shape of the structure and the position of the gas, oil and water interfaces. But the profile is still only a narrow band of information in one direction across the structure. To round out the picture, we now need to drill further outstep wells at right angles to the first three. Even with a classic dome-shaped structure, outstepping can have its disappointments. Nothing but water, and much lower down than expected. The rocks have slipped along a fault line, blocking off the reservoir. This is what's called a dry hole, a write-off, but its information was vitally important. We've now probed the limits of the structure, and at last we have a three-dimensional impression of the reservoir. We can now begin to plan its exploitation. To bring the oil field into full production, further wells will be needed. These are drilled into the oil-bearing zone beyond the edge of the gas, so we get the maximum assistance from both gas and water pressures in driving the oil to the surface. As more and more oil is withdrawn, we can inject water back into the structure to maintain the pressure by sinking more holes outside the limits of the reservoir. An oil field may extend over an area the size of a town, with a network of pipelines for gathering the oil and maintaining the pressures downhole. If the oil field were offshore, the whole installation, complete with pump house and treatment plant, would have to be concentrated into an area the size of a football pitch. To be economic, production drilling and oil recovery both need to be done from a central point, from a permanent platform set on the seabed. The oil reservoir is then tapped to the same pattern as on land by using the technique of deviation drilling. Oil reserves are nowadays being discovered in locations which are often difficult to develop. But wherever they exist, and however complex their exploitation becomes, our job is to reach them, to recover as much as we can, for as long as we can.